All right, so yeah, back to robots. Actually, I find it already very interesting, all the discussions we have, and what we see is a very, I think, multidisciplinary group of people coming together. And I hear a lot of similar things, but different terminology. And I'm going to throw a lot of terminology at you again from a robotics point of view, but I hope you bear with me and hope that opens at least a discussion that we can start to generate also a language that is exchangeable in a way. So I want to talk to you about physical intelligence. Well, our previous speaker already mentioned intelligence, and I love your definition of intelligent plants. I'm also going to push it to that edge, and also how that relates to the development of soft robots. Well, before showing you soft robots, it's of course always good to think about the idea we have about robots. This is probably you know this movie, or maybe you're familiar with similar movies of Boston Dynamics, and I mean these are very advanced tools that we are developing. They can dance. Maybe you even already start to feel that they are becoming similar to us humans. But luckily, we also had a movie this morning of this, and I'm going to show it to you again, right? It's already a little bit older. It's already 8 years ago, and since then, Boston Dynamics has had a lot of, made a lot of improvements as well. But when you put these kind of robots in these kind of complex environments, I mean, even already on sand, it's just very hard to interact with these, with basically the real world. So how do you have robots interacting with the real world? I'm going to wait until the last one. All right. Okay, maybe not. All right. So when we think about the natural world, there's very different ways of interacting actually with that world. And a good example is, of course, an octopus. And really, an octopus it doesn't have a centralized brain that does all the computing, but there's actually a brain inside each of its legs, besides, of course, that it's being squishy. And so what we often say is that this octopus has a sort of distributed intelligence. And this is quite still an advanced form of intelligence, I would say, because basically the arms, they do sense and they do have feedback inside them. And I always think probably the octopus, the central brain of the octopus, doesn't know exactly where every part of the tentacle is at all times. We've seen the divine arm today, or the fine hand. Well, imagine you have a hand that does something by itself. You might not have full control over. Well, maybe it's useful, maybe not, but it might be an interesting discussion as well. So when we think about this distributed intelligence, or as people from the soft robotics community sometimes call it physical intelligence or embodied intelligence, it doesn't really matter, but it's really thinking about where do we actually find the intelligence in the systems, and is it always in the brain, or is there much more happening as well? So for instance, if we consider an octopus, it's not only the tentacles, but also the fact that it's soft and it can adapt to maybe the environment and change its shape with respect to that. It's for instance, insects that store mechanical energy slowly and can release it quickly to make a jump. And you even see this in plants, where actually plants are able to create motions that actually the processes inside the plants couldn't do that fast. It's purely mechanical. So there's something inside this plant, and there's some, what we say, physical intelligence inside the system that allows it to interact with a more complex world than the real world. I don't know if I can go this far, but maybe even a tree in a way. When there's wind, there's an input, it does some computation, it bends, and it reduces the wind load because of its bending. So whether or not you want to call that intelligence or not, but it has evolved over time as a useful feature. And so what people now have started to do is actually mimic this kind of soft animals in order to create some robots with what we say physical intelligence. So here you have a typical soft robot. It's a pneumatic soft robot. So basically, it's a complex balloon. It has chambers. You inflate it, and by design, it will start bending, for instance. Now, there's also a lot of different kinds of soft robots that use, for instance, hydrogels, that uses materials, liquid crystal elastomers, that when you shine light on them they deform. and so forth. But this is something that we are playing with in the lab, so really the pneumatic side of soft robotics. And so the way it actually works is very simple. Effectively, you have what we call a soft actuator. You have chambers, you inflate it, and because the bottom has some fabric which is inextensible, you basically create a bending motion. And this is the principle of most of these soft robots, where you basically have a continuous deformation, and you have some design that will result into some form of motion. Now, what is essential here, and I've been talking about the physical intelligence, is the fact that if I now inflate this robot in a different environment, it will respond differently. So somehow, you could say there's some computation happening inside the system. There's some mechanical interaction, and if I can design this interaction properly, I actually can make robots that can interact in a useful way in a robust way with the environment. All right, it's quite dark, but this is, for instance, more of an application area where people are considering, so how can we use these soft robots? And what you see here is effectively a robotic hand. There's actually an end effector on that, which is a soft gripper. And I don't know if you can see it, but it's gripping different kind of objects. Now, the key here is that we're inflating these actuators all with the same pressure. So we don't do any change in our software. We just pick it up, give it a pressure, and it can basically handle all these kind of different objects just because the robot itself is deforming. Now, you can use this, for instance, in more sensitive tasks. So now you can sort of try to pick up a tomato, and normally if you would do this with a traditional gripper, you have to have sensing feedback, you have to control you have to know the size of the tomato, etc. In this case, basically you don't have to do that. And you basically turn on the pressure, and it can grip the tomato and hopefully not damage it. But there's also applications in medicine. And this is a very nice example of a previous collaborator, Ellen Roche, who's now at MIT. And she's basically trying to see, can we actually use this technology to interface with the body? So here what you have is also a pneumatic actuation system, and it's basically wrapped around a heart. And so what the system is doing, it's helping the heart to pump, right? And so it's helping, normally you would think about LVAD technology, so you have actually a rigid pump in your system that would pump the blood around. It's quite a difficult technology to do right because you damage, for instance, the blood. Here they're really thinking about different ways of interacting, having soft technology to interact with the body. Now we also started to go in this direction, and so about 5 years ago I was contacted by a cardiothoracic surgeon and thinking, hey, can we actually use this technology to build a fully artificial heart? And so we got funding, European funding, and we started to work also with tissue engineers along these kind of lines to think, okay, can we actually start to build a total artificial heart that would replace our own heart, right? And so it's really here that we thought, okay, this soft robotic technology can be key in really mimicking the natural behavior of the heart, so really the physiological contraction and the motion of the heart. And you can start to think about the heart as it has some actually intelligence itself as well. I hope I can now say this. And so there's actually a lot of mechanical regulation inside the heart. So there's something called the Frank-Starling effect. So there's a left and right pressure in the ventricles, and due to some mechanical interaction, it actually can balance those pressures very effectively without the use of our own brain that does this regulation. We're also working, as I said, with tissue engineers, and we're thinking we want this interaction with the blood to be as efficient or as natural as possible, and so we're thinking about in situ tissue engineering as well on these soft technologies. Unfortunately yet, it's not out there, so I can't talk about it now. Hopefully I can do this in a year or so from now, but we're making good progress. But I want to highlight one particular aspect that we've been focusing on, and that's actually mimicking the heartbeat. So how do we actually trigger the heartbeat inside the body, similar to how pacemaker cells actually trigger an oscillation in our body as well. And so given that the system has to be implanted in our body as well, we've been thinking, okay, can we do this without using any electronics to do that? All right, so that comes me to the ketchup bottle. And I can now talk about the physical intelligence of a ketchup bottle. All right? So you might have missed it. I can go back and forth. You know this, right? If you squeeze this ketchup bottle, nothing comes out, and suddenly a lot comes out. I don't know. And if you're bad, you hear a splash, and you're all covered in ketchup. But if you look at this, there's actually a few interesting behaviors inside this ketchup bottle. As I said, there's no ketchup, there's ketchup, and there's sputtering ketchup. But here you see an oscillation starting to appear, right? And in this ketchup technology, I would say this is not physical intelligence, it's just annoying, right? Annoying, right? So in this case, I would not call this physical intelligence. But what's actually happening here, right? And if we look now closer at a ketchup bottle here, if we apply a constant inflow into the system, this is a slightly altered version, what you get is actually it starts oscillating. So at a constant inflow, so I'm inflating this at a constant speed, the system by itself starts to oscillate. And actually it's called a relaxation oscillator, and it's very similar to maybe, for the somewhat older people here, the neon lights flickering. It's also a relaxation oscillator. All right, so we thought, can we actually use this kind of technology to start to create actually a heartbeat in the system without the need for any software, right? So can we do this without having a valve, control that valve electronically? And so here you see basically now our setup is basically simple. We have constant inflow, there's some precapacitance, here's the ketchup valve, there's a soft actuator here, and we have some outflow. And if you now just turn the system on, the actuator, which, as I can't show you, would be a heart in this case, actually starts to beat at a certain frequency. Now that frequency will depend on the amount of inflow we have, the rate of inflow in that case. So actually, thinking about how do you generate a heartbeat, well, this is actually all we need in this case. So we need a pre-volume to store some energy, we need the valve, and we need a heart in this case. And with those components, and of course we need some energy supply, so you still need a pump, you can create a heartbeat. But a lot of more fun things start to happen when you look at this system. So for instance, if we start to combine a lot of these systems, and I'm now moving outside of the scope of the heart application, but more towards soft robotics itself. So we were wondering what happens now if you put many of these systems in series, in parallel. And the interesting things starts to happen now, because you could say now there's actually more intelligence in the system. So in this case, actually, when we turn the system on, there's only energy inflow. You create an automatic sequencing in the system. And that's because there's some nonlinear mechanics happening that triggers this asynchronous actuation. What's also interesting now, you can start interacting with it. So if you see at some point, I'm squeezing the tube there, and you're actually changing the order of the sequence, right? So in a way, the system can be at multiple states, and you can change those states by interacting with it. And this is all without using any electronics. All right, so you can start to think about these systems more as electronic analogies and start to actually draw circuits. So here you have a more complex diagram that we thought, okay, if we make this, can we actually build robots that walk just by providing a constant inflow? So what you have here is a setup. There's 3 valves in this system, 4 legs. There's a pump. We just turn the pump on. And basically by doing that, the system will actually go through the sequence, and it will actually start to walk forward. Right? And again here, it's only a constant input. So really thinking about how do we actually program this behavior inside the mechanics of the system itself. All right? This is, for me, a very interesting domain, and for the group to work in, it's very playful. And there's a lot of things we can do with mechanics. But of course, in the end, you also need to start thinking about, and I think that's also good why we're here all together, and how do we start interfacing these different levels, all right? So I would say, yes, we probably need physical intelligence in systems. For instance, if we walk through the room, there's a lot of physical intelligence inside us that allows us to walk with sort of minimum input from the brain, right? Where maybe if you've seen the initial robots, they still need a centralized controller in order to get some motion, right? Now thinking about this physical intelligence, the first thing is how do you actually create that physical intelligence, and when is it intelligent? So nature has done that by evolution, we do it by design, and often it's still trial and error. So that's, I think, one big challenge we have here. But I think another bigger challenge is really how to interface this kind of body with actually more centralized control. So maybe we still need a brain that will say walk, and then everything else is embodied in the system. I don't know, so I'm very much open for discussions related to that in the coming afternoon and also tomorrow. With that, I'd like to thank the group. I didn't do any of this. These are the people that did all the work. Of course, funding. I've not been funded by Heinz. All right, and I want to thank you for your attention.